Hello guys, I am Anok Mondol, lecturer of Mechanical Engineering Department, Camellia Institute of Technology and Management. Uh, this is the second class of PCME 502. Um, if you want to understand this session, you have to watch the first session of this subject, that PCME 502 lecture 1. So today's topic is the state of stress at point. State of stress at a point. So we know that an infinite number of planes can be drawn through a point. We get an infinite number of stress vector acting at a given point, each stress vector characterized by the corresponding plane on which it is acting. So we knew that if this is a point, we can draw this plane, this plane, this plane, then this plane. So we see that we can draw an infinite number of planes through a point. Okay, so the totality of all stress vectors acting on every possible plane passing through the point is defined to be the state of stress at point. So the totality, the all total planes of all stress vector. So stress vectors in all stress vectors in all, the stress vectors at all plane in a point. So the totality of all stress vectors acting on every possible plane passing through the point is through the point is defined to be the state of stress at point. State of stress at given point. So we know that if the stress vector stress vectors acting on three mutually perpendicular plane passing through the point are known, we can determine the stress vector acting on any other arbitrary plane at that point. So we knew if the stress vectors acting on three mutually perpendicular planes, means xyz plane, passing through the point are known, then we can determine the stress vectors acting on any other arbitrary plane at the point. Okay, so let's discuss about normal and shear stress component. So this is the state of stress at a point. In previous class we studied about these stress vectors t1 t1 dash t1 t1 dash. This is the previous lectures material. So now we discuss that normal and shear stress components. So I turn the page. So I give the heading topic: normal and shear stress components. So at first I have to draw some diagram of this of a body. Let this is a body. This is the point. This is normal drawn from this point, and this is resultant stress vector. Let this is denoted by Tn, and this normal is denoted by N. Okay, so this stress vector we can resolve in two components, that is Txn and Tyn. Let this is the Txn and this is the Tyn. So Txn and this is Tyn. Okay, so let oh, this point, let this point is denoted as the P. So so what is Tn? Sorry, what is Tn? This is resultant stress vector. Resultant stress vector at point P. Sorry, at point P, acting on a plane. Acting on a plane whose outward drawn normal is N. N. So so this resultant can be resolved in two components, that is Txn, that is the horizontal component, and this is the vertical component, Tyn. So this n, this normal n, it can be also resolved in two components, that is at perpendicular direction and along the direction. So this, in this direction, this is along the direction of the normal, the stress is denoted as sigma n, and this is the perpendicular of this normal. So we can denote it as tau n. Tau n, okay, sorry, tau n. And this Tx can be also resolved in z components, this T resultant can be also resolved in Z components, that is TZN. Okay, so now the okay, what is N? N is N, I wrote it before. So now the component parallel to N is called normal stress sigma N, and the component perpendicular to N is known as tangential tangential stress or shear stress. It is denoted as tau n. Okay, so we have therefore the relation. We have therefore the relation T n modulus of T n square is equal to sigma n square sigma n square plus tau n square. Okay, where modulus T n is the magnitude of resultant stress. Okay, so as I told before, that this resultant stress vector T can be resolved in three mutually perpendicular components, that Txn, Tyn, and Tzn. So we have other relation, that we have other relation modulus of Tn square is equal to Txn square plus Tn y square plus Tn z square. Okay, so now we'll go the next another topic, that is so read this topic very carefully, that normal stress and shear stress component, that T is the resultant stress vector and N is the outward normal drawn from this point P. So T can be resolved in three components, that is Tx, Ty, and Tzn, and this N can be resolved into two components. One is parallel to this parallel to this N, along to this N, and perpendicular to this N. This is the along to this N, and this is the perpendicular to this N. So this stress which is along in the direction of the N is called the normal stress, and the perpendicular component or the perpendicular direction component is called the shear stress or this tangential stress. Okay, so read this very carefully, this all points very carefully, and we have some relations between the stress vector and normal stress and shear stress, that Tn whole modulus Tn whole square is equal to sigma n square and tau n square, and also Tn square is equal to Txn square plus Tny square and Tnz square. Okay, now we'll move in another topic, that is rectangular stress component. Rectangular stress components. At first we have to draw some diagram, some plane. This is plane, the three mutually perpendicular plane. This is x plane, this is y plane, and this is z plane. So let this is a body, okay, and let cut this body in parallel to the yz plane. So if this is the look, sorry, this is scale. So this is yz plane. So this plane is parallel to yz plane, means y. This is the yz plane. This is xy. This is a xy plane. This is yz plane. This plane is xy plane. This plane is yz plane, and what to say that this plane is this plane normal to look, this plane is xy plane, this plane is xy plane, this plane is yz plane, and this plane is xz plane. So you can see that this plane, look very carefully, that this plane is xz plane. Yz. This plane is xy plane, this plane is yz plane, and this plane is xz plane. Okay, so if we cut this body by a plane parallel to this yz plane, means this plane is yz plane, this plane is yz plane, this plane is yz plane. So we have to cut this body by this plane, yz plane, parallel to this yz plane, means if this is yz plane, so this is the plane parallel to the yz plane, where this, if this the direction of plane is the x-axis, and this is normal to the yz plane. Okay, look, this is the perpendicular or the normal drawn from the yz plane, and this is along the x-axis. So let normal, this is a point, and normal drawn from this point along the x-axis, that is in, and this is the stress vector, resultant stress vector Ts, suppose. Look, this x-axis is normal. This x-axis, this is, if this is yz plane, so this x-axis is normal to this x-axis is normal. This x-axis is normal to this yz plane. So this is also called this x-plane. If an axis is normal to the other two axis plane, means if x-axis is normal to the yz plane, so the yz plane is also called this also called plane x. So if z axis, from this diagram you can see that z axis is normal to this xy plane, so xy plane is also called the z plane. Okay, so let what is Tx? Tx, this is nothing but the resultant vector, resultant stress vector at point P this is point P. The component parallel to x-axis being normal to the plane as in the similar as in the previous diagram. We draw that the the component of stress along the direction of n is sigma n. So here we can write that is n, the stress component along the direction of n. So this is denoted as sigma x, and this is if this is three mutually perpendicular plane, so we can draw that this is tau xy and this is tau xz. So from previous diagram we see that this is the normal state which is acting along the direction of n, and this is the shear stress which is acting perpendicular to the direction of n. So similarly here the stress component which is parallel or along the direction of n is normal stress and denoted as sigma x, as this is situated, or the direction of the stress component is along the x-axis, and the other stress component which is along the y and z axis is known as a shear stress, because this is perpendicular to the n, and this is perpendicular to n, and this can be denoted as tau xy and tau xz. So you must be careful about the point that in above designation, you must be careful about it. In above designation, the first subscript x indicates the plane on which the stresses are acting, and the secondary subscript, the second subscript y or z indicates the direction of components. So you must be careful about this information, that the first subscript x that indicates the plane on which stresses are acting means sigma, tau xy. Suppose in case of tau xy, so tau x, the first subscript x, it is denoted as the tau is acting on xy plane, acting at x plane means yz plane, and the direction of tau is y. So tau xy, the significance of the tau xy is that the tau x, the first subscript x is indicate the first subscript x indicates the plane on which stresses are acting. So tau xy is acting on x plane, but the direction of the tau is y. So now similarly tau xz, in case of tau xz, the tau xz, the first as per the first subscript x, the tau xz is acting on a plane x means yz plane, and the direction of tau xz is acting on z direction. So now we have to draw that three mutually perpendicular stresses by using the diagram of a cube. This is x-axis. Sorry, this is x-axis, this is y-axis, and this is the z-axis. Z, y, x. So if I draw a cube, sorry. So we can draw, this is sigma x, this is tau xy, this is tau y, sorry, xz. Okay, at this plane, this is normal to the xz plane, means sigma y, and the perpendicular planes is tau y. Tau y means, because this is acting on y plane and the direction is x, so tau y, so we have to write tau y x, and this is what, tau y, because acting on y plane and direction is z. Similarly, this is also sigma y, this is what, tau y, sorry, the direction is this, and this is in this direction, because this is the negative value, so tau y x, and this is tau y z. So this component sigma z, here for the simplicity I write in this place. So this is sigma x and this is the tau xy, so in this direction tau xy, and this is tau xz, so in here in this direction tau xz is working, so this is sigma z, sigma z. So this is what, this in this direction, and that is in this direction, so this not here. Sorry, for the simplicity I draw in this place. So this is in z direction, this is in z direction, so x tau zy tau zx, and similarly tau, this is tau zy, this is tau zx, this is sigma z, and this is sigma z. So we can see that at any point P we can draw three mutually perpendicular planes, that xy plane, yz plane, and zx plane. Okay, and it is also known as x plane, y plane, z plane, because the yz plane is also known as the x plane, xy plane is also known as the z plane, and xz plane is also known as the y plane. So we can write that sigma x tau xy tau xz on x plane, sigma y tau yx tau yz on y plane, and sigma z tau zx tau zy on z plane. Okay, so this is, you can saw, this is the positive axis and this is the negative axis. So you you can see that this is positive x-axis, this is positive y-axis, this is sorry, this is negative x-axis, this is positive y-axis, this is negative y-axis, this is positive z-axis, and this is negative z-axis. So these values of this all stress are same, positive, but their direction is in their directions are varying in positive axis and in negative axis. So today's class end here. So today we have discussed the state of stress at a point. This is a point, and this is the multiple plane, or this is the infinite plane that can be drawn through a point. This is the state of stress. This, in all infinite planes, the stress vector, the totality of all stress vector acting on every possible plane is known as that's passing through a point is defined as the state of stress. So then I've discussed that normal and shear stress component, that this is the resultant stress vector, this is the normal drawn from this point, outward normal drawn from this point, the along direction, or the direction along the stress, the direction of stress that is along the direction of n is known as sigma n normal stress, and the perpendicular direction stress is known as shear stress, that is denoted by tau n, and this is the rectangular stress components, and this is the stress components drawn in three mutually perpendicular planes by drawing a cube. So this is the positive direction of plane, and this is the negative directions of plane. So the opposite faces are the negative directions of plane, and so in these all planes we can we can draw the three types of stresses in each and every plane. We can draw uh, uh, three types of stress, that sigma x, which is normal to this plane, and tau x and tau sigma, which is normal to this plane, and tau, and two types of tau, that is two other that the tau acting on the other perpendicular directions, that is tau these two tau is these two tau that that's acting at two other perpendicular direction. This is the shear stress, and so sigma x tau xy tau xz on x plane, sigma y tau yx yz on y plane, and sigma z tau zx and zy on z plane. Sorry, this is here. This is sigma x tau xy tau xz, sigma y tau yx tau yz, and sigma z tau zx and zy. Thank you.